Last time we got into, after we talked a little bit about, let me read just one more time. We got into really solutions, and remember, solutions really made up of two things, made up of the solute, which is the smaller part of the solution, and the solvent, which is the larger part. So for example, if we made our sodium chloride solution, the sodium chloride there would be the solute, and water, for example, here would be our solvent. When you put them together, it makes a homogeneous mixture where everything looks the same throughout. We also talked about one of the most sort of common concentration units that we associate with solutions, and that is molarity. Molarity, which is big M, is moles of solute over liters of solution, really, are just basically moles per liter. Remember, we could kind of use this to really solve for anything there. So if we wanted something like liters, once again, it is moles divided by molarity. If you want something like moles, it is liters times molarity. And again, this one, as we talked a little bit about last time, it is definitely important to make sure that you do convert your volume into liters when you're using molarity by itself. Otherwise, if you leave it, for example, in milliliters and you multiply it by molarity, you're actually not getting moles, but you're getting what is referred to as millimoles. So it is different. So you definitely want to make sure that it is converted into liters for sure. We also talked about the idea of dilution. And in a dilution, pretty much all you do is add more solvent. So in a lot of cases, people say add more water. Water, again, is a very common solvent, but not always the correct solvent in every situation. So there could be other things that are solvents that are used. But in a dilution, we add more solvent, which means basically the moles of the solute, which is really the stuff reacting, is equal to the moles of the solute afterwards, kind of before and after. So they really don't change, just the volume of the solvent, which is why the molarity goes down, because you're increasing the volume of the solution. So the molarity volume does drop down. We could use M1 V1 is equal to M2 V2. Once again, molarity and volume in both cases here, usually before the dilution and after the dilution. This is, again, one of those equations where you can leave it in milliliters, the volume here, as we talked about. That just means that when you do solve, for example, something like the volume 2, it would also be in milliliters. Or if you're dividing by the volumes there, they should both be in milliliters, and then it'll all work out. You could also change it to liters as well, and it will work out as well when you do that. But again, if you're using molarity by itself, definitely needs to be liters. If you're using this equation, you can leave it in milliliters, which is a common way of doing it. Also, a more generic version of this is sometimes used in books and stuff, which is C1 V1 is equal to C2 V2, where C is just concentration. And although, like I said yesterday, pretty much everybody uses molarity in most cases, you could use any type of concentration unit for a solution. So things like we'll talk about a little bit later on today, percent mass to mass, percent mass to volume, any type of concentration unit could technically be used in there as well. We finished up talking about the idea of titrations, which is a process where we use a burette and we add basically a solution to another solution, for example. And in this case, we typically add a solution of known concentration. So there's usually one known solution that we know pretty much everything about, the molarity, for example, how much volume we're going to use. And there's usually one solution where perhaps we don't know everything about it. And that's kind of what we're trying to find. We typically do a titration until we reach what is referred to as the equivalence point. And in an acid-base titration, what that means is the moles of the acid will exactly equal the moles of the base. So it's like that exact point where pretty much you have neutralized all the acid and base there together. There's pretty much all get used up at exactly that point. To basically recognize that point, we use something like an indicator. And an indicator is really, in a lot of cases, kind of like a weak acid. and it basically will change color depending on the pH of the solution. So for example, one we're using next week, and the most common one that most people use a lot of times is phenolphthalein, especially in the sort of chemistry classes. Phenolphthalein, for example, is colorless in acidic solution and neutral solution, but it does turn shades of pink within sort of the basic pH of around, for example, somewhere in the ballpark of 8.3 to 10, which is a basic range for a pH. And around the 8.3 mark, as we talked about a little bit yesterday, it's pretty much colorless, and then it gradually gets like a tint of pink, a little bit of pink, that you gotta like hold something up near it to kind of see the color. And then as you get closer to like the pH of 10 side, it gets really, really dark, dark pink. Some of you will see that next week, I think, when we do it. And again, and a lot of titrations, if you use this, we are actually looking for sort of that first faint sign of pink to occur. And that usually is indication that you're near the equivalence point in a titration that you would use something like phenolphthalein. It would turn somewhere in that early 8-ish range in terms of pH. So that's what you're looking for. So it's really important when you're doing a titration, as you do it, for example, if you had your base up here, like your sodium hydroxide and your acid on the bottom, as you keep dropping your base into your acid, you'll see the pink come and then it'll go away. The pink will come and go away. Gradually, the pink will stay longer and longer, and that indicates that you are getting closer to the equivalence point. And usually you kind of want to slow up on your titration as you're doing that, maybe a drop at a time or whatever it may be. And then hopefully you can sort of narrow in on it. Any questions on any of that stuff we talked about last time here? Okay, so putting together molarity and titrations and stoichiometry, we could talk about sort of solution stoichiometry. And in solution stoichiometry, it pretty much works the same way as normal stoichiometry. You basically still need your balanced equation. You still need to convert to moles. You still need to do the mole to mole relationship. And at the end there, usually moles to some other unit. So the main difference in sort of solution stoichiometry a lot of times is how we get moles. So a lot of the stoichiometry problems that we've done before, we use grams and the molar mass to get to moles, which you could still use in some solution stoichiometry problems. But most of the time, or a lot of the time, we use molarity here and volume. So a lot of times we're going to be using our moles is equal to liters times the molarity. So that is a very common sort of difference there, instead of using the molar mass, the volume, and the molarity there together. And on the back end as well, we also use sort of molar mass on that last step a lot to get how many grams we produce, which again, you could use as well in some solution stoichiometry problems. But at the very end here, a lot of times you will be in moles. And if we think about sort of molarity, which is moles per liter, this will usually lead you to calculating one of two things. You will either calculate the volume, which would be our moles divided by our molarity, or you may actually calculate the molarity itself, and you're given the volume to start with, and you use the moles to do that. So these are two very common sort of endpoints in a solution stoichiometry problem. And again, just slightly different there would be, sort of what we do with the moles at the beginning and at the end, instead of using molar mass, sort of using volume and molarity. You also can have a limiting reagent problem that involves solutions. So again, if you are given enough information about both of the reactants, either grams of volume and molarity, or volume molarity for each of them, and you could get to the moles of each of them, you would have to do a limiting reagent problem. So you definitely could still have a limiting reagent type situation that could occur with solution stoichiometry as well. Any questions on that there? So why don't you try this one here, see what you come up with. This is a titration problem. What volume of 1.42 molar sodium hydroxide solution is required to titrate 25 milliliters of a 4.5 molar sulfuric acid solution? So take a minute. Okay, let's take a look and see how we're doing. So we want to know, what is the volume of 1.42 molar sodium hydroxide? that's required to titrate 25 milliliters of 4.5 molar sulfuric acid. So obviously we have a base, we have an acid. This is what is referred to as a diprotic acid. Diprotic because it does have two hydrogens that it could give off. So when we have acids, there are ones that are referred to as being monoprotic. And monoprotic means that it has one hydrogen that gives off. Remember, what makes something an acid is that H plus. So that's the cation. That's what makes something an acid, the ability to make that in solution. So something that's monoprotic it has one hydrogen. So like HA, for example, that is a generic version of a monoprotic acid. When it breaks apart, it has H plus and A minus. So something like hydrochloric acid would be an example of that. H plus and Cl minus. There's diprotic acid, like we see there on our problem here. Also, you could use a generic formula for it, which is H2A. It has the two hydrogens that could come off, and that gives us two hydrogens overall. The difference, though, here is because H is H plus, the anion part of the acid actually has a -2 charge to balance it out. So something like what we see on this problem, sulfuric acid overall, when it does it, it does drop off two hydrogens and a sulfate. They, by the way, do come off actually one at a time. They actually both don't drop off at the same time. And there's also a triprotic acid, or sometimes referred to as polyprotic, diprotic, and triprotic, which is H3A. It has basically three hydrogens that will come off. Again, they actually do come off one at a time. But the difference here is the negative guy actually has a -3 charge. So something like phosphoric acid overall will drop off three hydrogens, again, one at a time. And the phosphate here has our -3 charges. So you'll sometimes see these sort of generic formulas used for acids, either being monoprotic, diprotic, or triprotic. And again, the important part is if you use one of those in an equation, that you understand what the actual charge is on the negative guy, as that will affect obviously the double displacement part when you put everybody together in the overall reaction. Any questions on that there? Okay, so we'll go back and take a look at our problem here, which is the diprotic acid. So obviously we have a reaction happening between our acid and base. And remember that when we do have a reaction between an acid plus a base, for the most part, you will get a salt and water, right? And the salt is an ionic compound, which again is where these guys as charges will come into play. And again, the water is made from the acid H plus and the OH minus there from the base coming together to do that. So that's where we will start here in this particular problem. We will start with our reaction, which is pretty much like every stoichiometry problem. We got to make sure we have that correctly. So we're going to take our acid plus our sodium hydroxide, which is our base. Once again, this falls under the big category of double displacement reactions, basically, as we talked about. So once again, the H is going to come over to the OH, the sodium is going to come over to the sulfate, and we want to make sure that we do write the correct formulas on the right-hand side like we talked about. So that will give us water, obviously, and that will give us some sodium sulfate, which is this guy here. Once again, the sodium +1, sulfate -2. Again, important, the sulfate being -2, like we talked about in our diprotic there. Obviously, the equation is a good place to start, but we also need to make sure that we have it balanced, and it's not balanced at this point. So we do need to lay up a 2 there, I think, and a 2 there, I believe. Any question on the equation there? The next thing we want to do is really kind of think about, what type of problem this might be. Is this a basic sort of stoichiometry problem? Is this a limiting reagent type problem? So to help us decide that, we could kind of take the information from the problem and see what we got to work with. For the sodium hydroxide, we have 1.420 molar, and we're really looking for a volume here at the end. For our sulfuric acid, we have 25 milliliters, and we are looking at 4.5 molar for that. So remember, for it to be a limiting reagent problem, you need to be able to get to moles of each of the reactants, which obviously is not the case here since we're actually looking for something of one of our reactants. We basically could only get to moles of this guy, so it really is just a basic stoichiometry problem at this point, which means what we're going to do next is frankly convert into moles. So the moles of H2SO4 are going to be found by using our molarity equation, which is our moles per liter. We have basically the liters and the molarity, so we're going to do our moles is equal to our liters. So we do need to convert our milliliters into liters divided by 1,000, or move the decimal place over. We're going to times it by the molarity of our H2SO4, which is 4.5 moles per liter of H2SO4. The liters here will cancel, and that will get us 0.025 times 4.5. 0.1125 moles of H2SO4. So again, very similar to a regular stoichiometry problem. The difference here is how we get to moles, volume, and molarity to do so. Once again, here we are actually not really interested in the H2SO4. We're interested in the volume of sodium hydroxide. So if we think about the molarity of sodium hydroxide, that would be moles per liter. We obviously are looking for the volume. We have the molarity given to us. So really what we need to figure out for the sodium hydroxide is how many moles that we have. And that is where the stoichiometry part comes into play. We now know the moles of H2SO4. So we could use stoichiometry here to go from moles of the moles of the H2SO4 to moles of sodium hydroxide. So really, this is like our second step or third step. From the equation, we see that for every 1 mole of H2SO4, you get 2 moles of sodium hydroxide. So we'll do the stoichiometry part here. 1125 moles of sulfuric acid. We want the moles of sulfuric acid on the bottom, and the moles of sodium hydroxide up on top. Those guys cancel, and we'll take this times it by 2, gets us 0.225 moles of sodium hydroxide. So that is the stoichiometry part, and that now gives us the moles for the sodium hydroxide. We also have the molarity, so we can now find what we're looking for, which again is a little bit different than at this point using the molar mass. So once again, here we're going to use molarity on the back end of this calculation. The liters would equal the moles divided by the molarity. So using our moles of sodium hydroxide, I'm going to use sodium hydroxide's molarity here as like a conversion. So again, that is 1.42 moles per liter. So I want liters is going to go up on top of sodium hydroxide, and our moles will go on the bottom. And that is our molarity basically. And we're going to divide by once, maybe 1.420. Going to give us 0.158 liters of sodium hydroxide, which is approximately 158 milliliters of sodium hydroxide. So this is, as you can see, hopefully really the same 4 steps as a basic stoichiometry problem here. Balanced equation, convert to moles, just differently using molarity and volume, do the mole-to-mole relationship, and obviously use a molarity here on the back end. Any questions on those steps there? Now, people will have the tendency incorrectly to use the dilution equation on these type of problems, that M1V1 equals M2V2, and you will get the wrong answer here because of the mole-to-mole relationship is actually not a one-to-one relationship. It will only work if you get lucky. It's a one-to-one relationship between the acid and base, then it will actually work, and you really shouldn't do that. So you should show always the equation and all that and do the problem this way. But sometimes people just fall into, I'm just going to use that equation, and you need to make sure you show the reactions and all that kind of stuff. So you'll get lucky if it happens to be one-to-one. You'll get very unlucky if it's not one-to-one, because this is not going to work out right for you at that point. Any questions on that there? Okay, so why don't we try another one here? Why don't we try, let's see. What is the molarity of KOH if 125 milliliters was neutralized by, we'll do 75 milliliters of 0.25 molar phosphoric acid. Okay, let's take a look. So we were looking for the molarity here of KOH, which is a base, and we're going to be neutralized. So basically like a titration problem. So sometimes when I'll straight out say titration, I'll say something like in an acid base situation, this one neutralized it or something like that. 75 milliliters of 0.25 molar phosphoric acid, which is an acid, obviously. So it definitely is going to be stoichiometry here. So we need our equations. So we got our triprotic acid here going to react with our base. So once again, this is going to be a double displacement reaction. We will make some water from the acid and the base, and we will make our salt, putting it together correctly. Potassium is +1, phosphate is -3. So we do end up with something like that as the correct formula. Once again, we're going to lay up some balancing here. So it looks like a 3 there and a 3 there. I think we'll do it. If we look at sort of the information given to us in this particular case, for the phosphoric acid, we have 75 milliliters, and we have the molarity given to us, which means we definitely could get to moles for this guy. For our KOH, we are looking for the molarity, and we have 125 milliliters given to us, which means we cannot get, obviously, to moles for this. So this is just, again, a basic stoichiometry type problem. The difference here is what we are looking for is we have the volume. We are looking for the molarity. So we are going to use the stoichiometry here to figure out the moles of the KOH. So to do that, we'll start with getting the moles of our phosphoric acid. So we do need to convert our volume into liters. So we need to divide by 1,000 or move the decimal place, 0.075 liters, timesing our molarity, which again, I'm going to get rid of the big M and use it as 0.25 moles per liter of H3PO4. So our liters here cancel, and we end up with here 0.075 times 0.25. 0.01875 moles of our phosphoric acid. Once again, we do need to get to moles of KOH to help us solve it. So we're going to go to the equation, and this is really, again, the stoichiometry part of it. And we see from the equation for every 1 mole of H3PO4, we get about 3 moles of KOH. Again, from the coefficients there from the balanced equation. That is what we're going to use to get us to moles of KOH, which is what we really kind of need here in this situation. Since we have moles of phosphoric acid, we're going to put the phosphoric acid on the bottom and our KOH up on top. Those guys will cancel, and that will get us 0.05625 moles of KOH. Any questions up to there? That again is sort of the missing piece that we need here to solve for what we're looking for. And that would actually be, in this case, the molarity of our KOH. So the moles that we just calculated, 0.05625 divided by the liters, which was sort of given to us, converting that once again into liters by dividing by 1,000, 0.125 liters. And in this case, we will end up with, see how I did making up numbers, not too bad, I guess, 0.45 moles per liter of KOH. Or again, you can just write it as 0.450 big M KOH. Any questions on any of those steps there? And again, it's still really the same 4 steps that we talked about with basic stoichiometry problems. Step 1, balance equations. Step 2, convert to moles. Step 3, use the mole-to-mole relationship. And again, in this case, convert those moles into some other unit, which happens to be molarity in this case. So really the same 4 sort of steps along the way. Any questions on any part of that there? So these are really solution stoichiometry problems. They're really just stoichiometry problems involving molarity and volume, and they're also sometimes referred to obviously as titration problems. So typically in a stoichiometry problem, wherever you have kind of like an acid and base together, is sort of usually like a titration sort of problem that's happening, because that's usually the common way that you add one to the other is through a titration process using the Virat and all that we talked about. Any question on titration type problems? Okay, let's try one more sort of solution stoichiometry problem, not necessarily a titration problem, but a little bit on the relationship of what we talked about before we saw that slide on titrations, the gravimetrical analysis, where maybe you make a precipitate and you want to figure out how much precipitate you make, and that can happen by mixing 2 solutions together. So let's say we took, let's see, what do we take here? Let's say we took 25 milliliters of 0.5 molar barium nitrate is mixed with, we'll go with 20 milliliters of 0.75 molar sodium sulfate. How many grams of barium sulfate would you produce? All right, so why don't you give it a try first and see what you come up with here. Again, it is a stoichiometry problem. Might need some numbers here. So barium, I think, is hard to read there, 137.3. Sulfur 3207, and oxygen 16. All right, let's take a look. So we're mixing 25 milliliters of our barium nitrate with 20 milliliters of our sodium sulfate, and we're going to produce obviously barium sulfate. So obviously we need a little reaction going on here. So it would be our barium nitrate, which we do know is a solution since we're using volume of it, plus our sodium sulfate, which is also a solution since we're dumping 20 milliliters of it. And they told us we will produce barium sulfate, which we're assuming is a solid since we're looking for grams. This obviously is a double displacement reaction, which is where the barium sulfate comes from. That means our sodium and nitrate should come together. Once again, it should come together properly as NaNO3, not Na2 or anything like that. At this point, we have all the correct formulas together, like we talked about with balancing. We could go back now and balance the equation. So a 2 there, I think, and that might do it if I'm not mistaken. So that's 2 sodiums, 2 nitrates, a sulfate, and a barium there. Any questions on the equation? Now let's see what we are looking for. We're obviously in this case looking to our product side here to figure out the grams. We are given in terms of barium nitrate 25 milliliters, and it is 0.5 molar. Obviously we can get moles from that. For our sodium sulfate, we are given 20 milliliters and it's 0.75 molar, which we also can get moles from. Is this a limiting reagent problem? This is. We have enough information actually to get the moles of each of those things. So obviously we do need to do a limiting reagent type problem in this situation. So to do that, we obviously need moles for each of those guys. So that's where we'll start. We're going to go with the moles of the barium nitrate. And we will use our volume and molarity to do that. Converting our volume into liters, dividing by 1,000, or moving the decimal place there gives us 0.025 liters. Using our molarity without the big M there, 0.5 moles per liter. And that is going to get us 0.5 times 0.5. Looks like 0.0125 moles of barium nitrate. We'll do the same thing for our sodium sulfate here. So the moles of our sodium sulfate. Also converting the volume into liters, which we do need to do here when using it with molarity by itself. We're going to times it by the molarity as moles per liter. Liters, once again, cancel on both of those guys. And we end up with here 0.015 moles of our sodium sulfate. Any questions up to there? So because it really is a limiting reagent problem, I'm going to do the ice table approach. Again, you could use a different approach if you like that better. So I'm going to go to the next page here and do that, I think. So we have rewriting this guy here, barium nitrate, plus some sodium sulfate. So barium sulfate, that is definitely not barium sulfate. Try that again. Not sure what that is there. All right, try that again. All right, take 2, barium sulfate. That's a BaSO4. There we go. And a little sodium nitrate. And I should have a 2. So doing our ice table with our initial moles here, we had, I believe, what was that there? 0.0125. And our other guy there was 0.0150. Once again, we could assume 0 of each of these guys on our product side. We will do our change, which would be minus x plus x, and plus x, bringing us to 0.0125 minus x, 0.0150 minus x, x, and x. Any questions on the table here? All right, as we talked about when we were doing this, we're going to set each of these equal to 0, which pretty much gives us the same number. So 0.0125 minus x is equal to 0. X equals 0.0125 moles. Same thing here. This basically gives us an x is equal to 0.015 moles when we set it equal to 0. At this point, we're looking for the smallest number, which looks like it is barely this guy here. So we'll go with that. That x, once again, is all the x values in this table. And in our case here, we are interested in barium sulfate. So we see that the moles of barium sulfate will equal x, which means it is 0.0125 moles of barium sulfate. which we could then convert into grams by using the molar mass of barium sulfate. So barium was 137.3. Sulfur 3207 plus 4 times 16 for the oxygen gives us about 233.4 as the molar mass from the periodic table. And that would get us about 2.92 grams of barium sulfate would be made in this particular case. That would once again be our theoretical yield here in this particular problem. So this again demonstrates, with any type of stoichiometry problem, regardless of sort of what you're given in solutions or grams, you can have that sort of limiting reagent situation pop up as well. Question on this one here. And again, as we talked about before, if you wanted the sodium nitrate, you should do the table correctly, unlike I did there. That actually should be 2x because the coefficient is a 2 there. I forgot that. So that would be 2 times x. Any questions on stoichiometry involving solutions? Sounds good. All right, then what we're going to talk about is some other sort of concentration units, although molarity is really sort of the most common unit that's used. There definitely is a number of other units that we use for solutions. One was referred to as percent by mass, or sometimes also referred to as mass percent. So this is sometimes referred to as the mass percent, and it's sometimes abbreviated like that, percent m/m. And it is the mass of the solute over the mass of the solution. And especially in these type of problems, it is the bottom part that's really important. It is really the mass of the solute plus the mass of the solvent. The reason why that's important is because in a lot of these type of problems, they will give you that information separate from each other. So they'll tell you the mass of the solute. They'll also tell you the mass of the solvent. And it's a very common mistake that people make is they just kind of roll with the solvent, which is a larger number on the bottom there, but you do need to get them together. Make sure you do have the mass of the solution. Any type of percent concentration unit, you could convert into sort of a usable number. So for example, if we had a 4.5% by mass sodium chloride solution, what that would mean is you essentially have 4.5 grams of sodium chloride and 100 grams of solution. And you could really use that as sort of a conversion factor. If you needed it the opposite way, you could do 100 grams of solution is 4.5 grams of sodium chloride. So, sometimes you are given the percent composition or the percent by mass there of a solution, and it's sometimes easier to kind of use it as a conversion factor and doing that. Here we assume 100 because it keeps the numbers all the same when you do it. There's also some other sort of percent concentration units that you sometimes come across, and that is percent volume to volume, and that's volume to volume percent. And that is percent volume to volume is the volume of solute divided by the volume of solution times 100%. So unlike sort of percent mass to mass, this one, you usually don't have to worry too much about the volume of solution because that's usually just either given to you in the problem. It's not usually broken up. The other percent concentration unit is percent mass to volume, and that is the mass to volume. And that is the percent mass to volume is the mass of the solute divided by the volume of solution times 100%. So it's kind of like this guy here is milliliters over milliliters. This one is grams over milliliters, kind of like density, basically. And the previous one is grams divided by grams, typically speaking. So you could, again, for all these guys, convert them into usable sort of conversion factors. If you have the 4.5% volume to volume sodium chloride, that would mean you had 4.5 milliliters of sodium chloride and 100 milliliters of solution. Or again, you can use it the opposite way, 100 milliliters of solution, 4.5 milliliters of sodium chloride. And same thing here, if you had 4.5% mass to volume, it would be 4.5 grams of sodium chloride and 100 milliliters of solution. Or in 100 milliliters of solution, there is 4.50 grams of sodium chloride solution. So sometimes it's really easy to use these as conversion factors when you're doing problems and really just kind of take a dimensional analysis sort of approach. You also, in any of these, can basically just stick them into the equation and solve for it like a normal sort of formula. But sometimes the dimensional analysis approach is a little bit easier to sort of do. Any question on those three there? Okay, so why don't we try one here? A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass to mass. Okay, let's take a look. So we're looking for percent mass to mass here, and that is the mass of the solute divided by the mass of the solution times 100%. So we're taking 2.5 grams of calcium chloride and mixing it with 50 grams of water. So our calcium chloride here is the smaller part, and that would be our solute. The water here is the larger part, and that would be our solvent. So the mass of the solute would be our 2.5 grams. The mass of the solution would be the 2.5 grams plus the 50 grams there of water. Again, important to get them both and not just the solvent by itself. And if we do that, we will end up with 4.76% by mass of calcium chloride. Any questions on that one there? Basically, we have 4.7 grams of calcium chloride for every 100 grams of solution in this case. So I'm going to try another one. Concentrated hydrochloric acid solution contains 37.2% by mass hydrochloric acid. What is the mass of hydrochloric acid? That's contained in 35.5 grams of the concentrated HCl solution. We'll help you out there. Okay, so looking at this one, we have the percent mass to mass given to us. So we're looking for the mass of the solute, mass of the solution, times 100%. So you could definitely kind of put everything into this. Since we do have this given to us, we do have the mass of the solution given to us, and you could obviously rearrange it and solve for the mass of the solute, which is the HCl in this case. A reminder that the name of the solution, as we talked about last time, is really what the solute is. So the solute is really the name of the solution. So if we have a hydrochloric acid solution, hydrochloric acid here would be the solute. We could also take the approach, since they did give us the percent mass to mass, which was 37.2% mass to mass. We could convert that into a conversion factor and kind of use it in a dimensional analysis approach to the problem if you wanted. That would have been 37.2 grams of HCl and 100 grams of solution. Or in 100 grams of solution, there would be 37.2 grams of HCl. So since we know the grams of solution, we could, if you want to take a dimensional analysis sort of approach, you could just do it like so, using the conversion factor where the solution will cancel out. And we will end up with about 13.2 grams of HCl. And by the way, that is obviously the exact same math that you would do if you rearrange this equation and solve for the mass of the solute. Any questions on that one there? All right. All right, another sort of concentration unit that we come across, and we will see it later on in one of the last chapters we talk about, and that is molality. Molality is little m, so not mass when you see the little m in this situation, and it should not be confused with what we were talking about earlier, which is big M, which is molarity. And again, big M is moles per liter. Little m is molality, which is moles of solute over kilograms of solvent. So molality is moles of solute over kilogram of solvent. It is abbreviated molal, kind of like molar is abbreviated. The one that kind of links these two together, if you ever need to kind of go between these two, is usually density is kind of the thing that kind of links those two together. If you kind of have to go from one to the other, is usually what you do here. So this is moles per kilogram is the units that you are left with are much like molarity. You can't leave it as little m in terms of the units at the end of it as well. Also, much like molarity, you know, if you're going to do a calculation, you might want to convert the little m into these two units so you can see both of the units as you're doing the calculation, so none of it gets lost. So why don't we try one here? What is the molality of a solution prepared by dissolving 61.7 grams of C3H7OH in 175 milliliters of water, and carbon is 12.01. Hydrogen 1.008 and oxygen 16. All right, take a minute to see what you come up with here. Okay, so again, molality, which is little m, is our moles of solute divided by our kilograms of solvent. And in this case, since we're dissolving this guy, which would obviously be a solid, that would then be our solute. Once again, here, water would be our solvent. So in order to get to the moles of the solute, we do need to convert it into moles by taking the grams and using the molar mass from the periodic table there. We got 3 times 1201 times 1.008 plus a 16, looks like a 6009. We're going to divide by 6009 grams per mole. And that will get us call it 1.027 moles of C3H7OH. That is the top part. The kilograms of solvent, in this case, they gave us 175 milliliters of water. We do have the density of water given to us, so we could use that to get to grams, which is not too much math here. That will cancel, and that will give us 175 grams of water, which is our solvent. We do need to convert it into kilograms, so there is 1,000 grams in a kilogram. So those guys will cancel, gives us 0.175 kilograms in this case, which would be the bottom part of what we need. So the molality would be 1.027 moles up on top, 0.175 kilograms on the bottom, and that will get us looks like 5.87, and it would be moles per kilogram, or 5.87 little m in this particular case. Any questions on that there? Okay, so that is molality, and again, we will see it a lot when we talk about colligative properties in one of the later chapters there towards the end. It is a number of sort of formulas that are used for colligative properties of solutions, things like boiling point elevation, freezing point depression, those type of things. Last sort of concentration that we're going to talk about is what's referred to as a mole fraction. And much like it sort of sounds like, the mole fraction is basically the fraction of a particular mole of a substance over the total moles in this solution. So it's not really a percentage, so we don't multiply by 100, but we basically can calculate the mole fraction by taking, and the X represents the mole fraction sometimes. Basically, you take the moles of the substance you're interested in, divided by the total moles there are. And again, here we don't multiply by 100. So when you have maximum mole fraction, you all should add up to 1, basically, in this case, since we're not multiplying by 100 in this particular case. So let's take a look at one here. Calculate the mole fraction of methyl alcohol in a solution that's composed of 0.328 moles of methanol and 0.929 moles of ethanol, basically. So if we wanted to figure out the mole fraction here of our methanol or methyl alcohol, it would be the moles of our methyl alcohol divided by the total moles. So in this case, that would give us 0.328 moles divided by 0.328 plus 0.929 moles, which would be our total moles. So we'll take that, and once again, here we're not going to multiply by 100, so it's not really a percentage, even though it's sort of like a percentage. Will give us basically 0.261 in terms of that as our mole fraction there for methanol. We could, if we wanted the ethyl alcohol, do the same calculation, which would be the moles of the ethyl alcohol 0.929 divided by our total moles. And again, not multiplied by 100. Gets us 0.739. By the way, since this was 100% of everything, we could have took 1 minus 0.261 and got us there, since that was the only other thing left. Kind of like when you take 100 minus something, it'd be the same idea if it was a percentage. A question on mole fraction, which we will also see in the next chapter, which is gases, and we will see at the end as well in colligative properties of solutions. Any questions on any of that stuff there? All right, that wraps up, I think, this multiple sections of stoichiometry from different places. And we will lay it up there, obviously.